One of the biggest victories of modern physics is our understanding of the structure of the atom. And one of the best ways to learn the evolution of this understanding is with this PhET-Sim models of the hydrogen atom. It's got two modes, experiment and prediction. Experiment is what really happens. So if you do the experiment, this is what happens. So the first thing you do is you turn on the light gun. We're going to send in some white light. Inside this box is an atom. We don't know yet what that atom is. We don't know what it looks like. We know that they're there, but we don't know exactly what it looks like. And so this is what we're trying to do. We're shining light through the atom, and we're getting out a different pattern, right? So some of these, you saw that one bounce off. Some of them change color. There's all this different stuff that's going on there. Something is going on inside this mystery box. There's a few things you can change with this. You can change it to a single wavelength. So you might send it through the ultraviolet. You might adjust that a little bit. Ooh, something got kicked off there. You could take it up to visible. If you want a sneak peek of what the answers are, you can click on this to see the absorption wavelengths. We won't peek ahead there. I'll let you discover that. But anyway, this is just like what you do in an experiment. You could also collect information in a spectrometer. So you could use this to see what happens to all that light that's going through. And eventually this will fill up with data about what light passes through and what light gets bounced back like that. You can even take a snapshot here with the camera, it looks like. So anyway, this is the experiment. So the idea is that you go through this little activity and look at the experiment, try to get an idea that something weird is going on here. Why does some light bounce back and some light go through, right? That's what I believe you're supposed to wonder here. Then you click on prediction. This is one of the best parts because this shows you what would happen if each of these models of the atom were true. And basically when you go from top to bottom, you go from classical to quantum. You're going through the historical models of the atom. So at first we thought atoms were just these solid balls there somewhere in the material. And you can see if it's a solid ball, then all of the light is just going to bounce back. Clearly not what happened in the experiment, right? You go back to the experiment, wait a minute, whole lot of these are going through. Clearly here, most of them are bouncing back. Anything that goes in that box is getting bounced back. So something's wrong with that. Then you move up to the plum pudding model. This was the idea that there's some positive charge here and a negative charge in the middle. Well, if that's the case, then this light should be accelerating the negative charge and you should be getting an outgoing pattern like this. This is a little bit better, right? And the goal is for each of these models to get progressively better. Here's the classical solar system model. What happened to that atom? Let's actually slow down the animation to see. What's happening here is you've got the electron orbiting around the proton, just like you see probably in your high school chemistry and even physics textbook. What's going on with this explosion? Well, one of the predictions of classical electrodynamics, and it's unfortunate that most intro E&M classes don't get to this because it's a bit complicated. But one of the predictions of classical E&M is that an accelerating charge is going to radiate out electromagnetic fields. An electron going around in a circuit is accelerating, right? Centripetal acceleration, v squared over r. Therefore, this thing should be giving off lots and lots of radiation. The energy for that radiation has got to come from somewhere, right? Conservation of energy. The energy has got to come from somewhere. That's what you're seeing here, is that the energy is decaying. Right? So the energy is getting lost. The energy is going out into the radiation. It doesn't have as much kinetic energy. It's going to fall in. And eventually it's just going to collapse. And this happens on the order of nanoseconds, femtoseconds. I forget what the number is. But it's really short. Like the universe would have imploded on itself by now if this simple model were true. And yet this is the thing we show you in textbooks. Oh, goodness. You can come up here to the Bohr model. This is getting even better. Let's bump the speed back up here. This is getting a little bit better because this is showing the electron jumping between these different levels. You might notice it goes to different levels based on the color of light that's coming in. That's interesting. It's almost like the energy of the light depends on its wavelength or frequency. You come up here to de Broglie, and things get even more interesting because now instead of an electron going around an orbit, it's the orbit itself is kind of oscillating and perturbing. You get these really neat wave patterns here. So now we've gone from an electron as a particle to an electron as a wave. Here's what that looks like in 3D. Here's what it looks like in terms of a color shading. Did we have that on the board? We did not have it on the board. Okay. Finally, come down to Schrodinger. This is the most quantum of them all. This is this probability cloud changing as the light interacts with it. And you can see what's happening to the energy levels as it goes around. You notice the energy level diagram is getting more complicated as we go through. At first, we don't have any energy because there's no electron there. Here we don't have an energy because it's just oscillating. Here we finally get some energy, and it's just kind of plummeting down. Here the energy has these nice little staircase levels, and you notice that the electron is going to end up jumping up there. See, we get a jump up there and then a fall down. And de Broglie is about the same thing. It's the electron itself that's changed. In Schrodinger, though, the nature of the electron has changed and the energy levels have changed. So you get all these L values in addition to these N values. So I encourage you to play around with this. If you're in my class, we'll have an activity for you to explore each of these. And basically your goal is to figure out how does each of these become better? How does each of these match the experimental results better as we go on? Because this is, again, this is the big demonstration that quantum mechanics is the fundamental reality in the universe, not classical.